All right, let's get going. Hi, everyone in the internet. Can you hear me? Can I get a thumbs up if you can hear me? Cassie, are you able to hear me? Yep, thumbs up. Eldrin, how's it going? Okay, thank you. Let's get going. So first thing I want to do is finish up, angle this. Do that. Anyways, I wanted to finish up what we were talking about to complete homework 5, and then we will move on to a little bit of test review with whatever time we have left, which should be plenty because there's not that much more to do in homework 5, I don't think. So let's just jump in at the beginning of problem 2. We talked about how to solve the first couple parts of this or so, but we'll just briefly touch on that and get into the new parts. Okay. You are measuring the response of a room that has dimensions Lx, Ly, Lz equals 5, 4, and 3 meters. During your measurements, you measure a large resonance at the frequency of 57.17 hertz and are assigned to build a bass trap to compensate for this. Your design will look similar to the one shown below. To choose a location for the bass trap, it is necessary to figure out which mode of the room is problematic. For these dimensions, which normal mode has a frequency closest to the observed value? So here's your equation. And you can, there's nothing you need to do here except for just plug stuff in and then iterate through values of L, M, and N. You can do this in MATLAB, that's the way I would recommend doing it. I made myself a little array of like the first 7 modes is what I did. Don't worry about going to like L equals 99, M equals 0, and or M equals 0, N equals 0. That's not going to be the answer, right? Don't let your numbers get higher than 2 at the absolute most. So, or I guess, start from the bottom and, stop when you get there. But the point is it's a pretty, it's a lower frequency, which would make sense that it's a pretty lower order mode or however you phrase that. You guys all okay with that? That's fine. Yep.
The frequency I got was the lowest frequency I got was well above this given problem frequency.
Let's look at that after class because that's not right. Okay. That's a math error somewhere. But we can look at that together. Is that cool?
Yeah.
I mean, check are you doing it in MATLAB? Yeah, I would check your code, but look, we can look at it together. Cool. But it's a good question. You should definitely see something below there, right? Okay, you decide the best way to compensate for this mode is to build a bass trap along one wall of the room. What is the surface area of the wall you will choose, i.e., which wall is it? So let's talk about a hypothetical here. So let's say I find that the mode I'm interested in is 1, 0, 0, okay? And let's call this dimension X, okay? This dimension going this way. So what that means is I have half of a cosine in terms of pressure going from this wall down to here. It's got a maxima over here, right? And it's at -1 over here on that wall. Can you envision that? Is that okay? Right? In the other 2 directions, it does not, it doesn't change with either of those directions, right? There aren't waves in those directions. So let's think that through. So the YZ plane is the one that goes like this, like that, straight up and down, right? And those planes, right, are always going to be the same pressure. If I draw a plane like this, everywhere on that plane is the same pressure because it doesn't change with Y or Z. If I draw a plane like this, everywhere along that plane is the same pressure, right? Because it doesn't change with Y or Z. The only way that it changes is in this direction. Cool? Okay. So where do I want to place my bass trap? I got 2 choices that make an equal amount of sense here. Where do you guys think? Again, my wave, my half cosine is in this direction, which we're calling the X direction. So where are we going to put our bass trap? Like that wall in that wall?
Yeah.
Totally, right? Yeah, I mean, we're looking for an antinode, right? That's always where we want to like take energy out of a system or put energy in. And those antinodes exist at these two walls, right? There's nothing here, right? There's nothing here. So yeah, absolutely. So that's what you're going to do. Find the mode, find out what mode it is, and then just think that through. Basically, what walls is that wave touching? Is maybe a way to phrase it. Does that feel okay? Can you figure it out? Is that cool? Yeah. Okay. All right, guys on the internet, if you have questions, please yell at me. I will stop. I could draw something here, but I would try to draw something in 3 dimensions, and I would do a bad job. So we're not gonna. Okay. To construct the base trap, you will add a second wall behind the original wall so the dimensions remain the same, and drill a number of holes in the original wall similar to the picture above. Assume the original wall is 1.5 inches thick and the new wall leaves an air gap of 1 foot behind the walls. How many 2.5-inch diameter holes do you need to drill in the original wall to eliminate the 57.17 hertz tone? Okay, so this is a Helmholtz resonator, is what this is, right? The professor drew this in class. You have this in your notes, but that's what we're talking about here. The neck of this Helmholtz resonator is those holes, those little cylinders, right? In the new wall, in this case. You with me? The body, is that what they call it? I guess, right? The body of the Helmholtz resonator is that space behind the new wall, or the old wall and the new wall. Wait, which one's new? Sorry. The new wall, you build a second wall behind the original wall. Yeah, okay. So the old wall is the first one, and that's where the neck holes are, and the new wall is the one behind it. And the area between those two walls, that's the body of this Helmholtz resonator. So I got an equation here for you. And it's going to tell you the resonant frequency, and what you have to give it is the speed of sound in the medium, which in our case is just air, so 343. The volume of the air gap, so not the neck here, we're interested in the volume of the air gap. And what that's going to be is the area of the wall, right, multiplied by the depth of, or the distance between the new wall and the old wall. Can you guys picture that? That makes sense, right? Make sure you convert to SI units probably before you do anything. That's probably the easiest way to screw this up, right? You're given inches and feet, and just get those all into meters, okay? But that volume, here, let's write that out. That volume is area of wall times the distance between old and new walls. Okay. The surface area of the neck, right? So this is what's going to get we're going to multiply by this by a factor of n, right? This is what's going to tell us how many of these holes I need to drill, right? So the surface area of the neck is going to be pi r squared. You're given a diameter, not a radius. Make sure you do all those conversions correctly. That's all easy to screw up. But find the front face of that hole. It's pretty easy, right? And then in your equation, it's going to be n times s. N is what you're solving for. How many of those do I need to drill, right? The s itself won't change. That's going to be the same for each hole, right? Number of holes. Yeah? So let me get through it, and then we'll talk questions if we need to. And then L is just the length of the neck. The length of the neck is not going to change, right? Doesn't matter how many you drill, right? The length of that neck is the width of the old wall, right? Yeah, right. So the original wall is 1.5 inches thick, right? So that is that length of the neck. Okay. That I think about gets you there. The only way this isn't just a straight Helmholtz resonator question that's really straightforward with all this stuff is that you need to do a little bit of math to figure out that surface area. You need to do a little bit of math to figure out that volume. You just need to do a unit conversion to figure out that length. You're given that. And then you have this factor of n, which is what you're actually solving for. How many of those do I need? How's that feel?
For the surface area.
Mm-hmm. Imagine looking at that hole straight on.
Yeah.
Right? The surface area is that circle.
Oh, just like the.
Just the circle, just 2 dimensions. It's just pi r squared, where r is half of that diameter you're given. Does that feel okay? Cool. Yeah, because that surface area, if I have 15 of those, right, the length hasn't changed at all. The length of the neck is always the width of that wall, but the total surface area is however many holes times the surface area of 1. Yeah. Everybody else feel okay about that? Internet feels okay? Oh, Eldrin has a question. Is that surface area times the number of holes? Yes. Yeah, the big S is surface area, and that's where your factor is. The how many is just multiplied by that surface area. And the surface area, just to be clear, is just this. We're looking at this hole straight on, right? We know the diameter is what, 2.5 inches. So I'm looking right at the wall now, 2.5 inches, right? So pi r, which is d over 2 squared. Yeah. S equals pi d over 2 squared. So just convert that 2.5 to meters and plug it in there and you're ready to go. Cool? Okay. Yeah, Eldrin, that feels okay to you?
Yep.
Sweet. Okay, I'm leaving it there, but if you're marinating on this as we're doing other stuff, we can absolutely come back to it. Let's jump to question 3, the last question. And again, we did part of this, but we're going to come back. Bless you. You're hosting a concert in your parents' basement with a carpeted floor and concrete wall ceilings. The basement is rectangular with width 8 meters, height 2.5 meters, and length 12 meters. Estimate the total number of modes that resonate between 0 and 150 hertz. We have an equation for this. It's a statistical thing. We talked about it in class. Remember, those modes get closer and closer together as you get higher and higher, right? We did that animation in class where you saw that. But here's your equation. The F3, that is F cubed. It's not like F3 is some like the 3rd frequency or something like that. Those are both cubes in there. There's nothing to that one, run that equation. That's your answer. Okay on that one? If you want a better why explanation, go look at those notes from class. But it's basically that idea that the modes just get closer and closer together, and you can do a statistical analysis on it to see how, what that mode density is, and you can extrapolate how many you expect to see. But it is an estimation, right? Not always going to be true, because it's going to depend a little bit, at least, on those the different dimensions, right? Because you can have the same volume and have it split up into different size walls. Let's talk Schrader cutoff frequencies. what is the Schrader cutoff frequency for this room if you measure T60 to be 1.7 seconds? Just a quick aside here. Sometimes we talk about T60 at certain frequencies. You've seen this before. At 250 hertz, the T60 is 1.7 seconds, right? When you see it like this, T60 is 1.7 seconds, we're assuming that that's true for every frequency of interest. So maybe from 20 hertz to 20 kilohertz, right? It's the same. That's not actually true really ever, right? Because absorption coefficients are frequency dependent, right? And if you ever really measure a room, they do these neat waterfall plots. So you can see, I wish I had one to show you. Maybe I'll pull one up later. You can see what the decay time is per frequency. It's a 3D plot, right? So you can see like, oh, at 80 hertz, right, the decay time is 2.5 seconds. But by the time you get to 1K, our absorbers are working better and it's only 1.9 seconds. You know what I mean? It is very much frequency dependent, but when you see it like this, you're assuming it's not. Okay. When you treat a room in real life, you'll be doing it on a per frequency basis, right? You're interested in frequency response because of the modes, right? Does like the, low E on an upright bass, does that sound really loud at the listening position or whatever? That's a modal problem, right? Constructive interference or whatever. And then you also have like decay per frequency. You want things to be relatively even as to how they die out. Anyways, that's an aside. This would be a broadband kind of thing. So our Schrader frequency is 2000 times the T60 times root T60 over V. Done and done, right? He doesn't ask you this here, but I want you to know it for your test. What is the Schrader frequency? What does that actually describe? My fault. There's two regions, if you can remember the names of either of them.
I can take what I have in my notes.
I'll take it.
It is the frequency where the transition occurs between modal and statistical response regions.
Yep, I'll take it. That's perfect, right? And basically, it's not this hard. I mean, he's defined it as some hard line, but it's obviously a spectrum, right? And what we're talking about is this area of the room response where we can clearly identify these modes, right? That's the, I don't know, that's the 0-1-1 mode, right? Rearing its ugly head. I can see that in the frequency response. It goes like this, right? Or whatever, right?
The chat in the screen spot.
Oh, my fault. Dang. Amateur hour over here. How about like this? Let's draw it better. So there's my frequency response when I'm looking at this mode in particular. I can really see it there. It's clear. When I get past that Schrader frequency, the modes are so close together, I can't really see that anymore. They're all on top of each other. There's so many modes so close together that it does the response doesn't look modal. You can't point to that peak and be like, that's the 1-0-1 mode, right? They're all next to each other, and it just looks like kind of a constant, right? All mixed up. There's a better drawing of this in your notes, but I guess judging by people's kind of like, how you look right now, I would recommend looking at those notes. It's an important concept. So just to repeat myself, the Schrader cutoff frequency is this transition point. Let's call it on this map here. F Schroeder, is that really how you spell that? Schrader. It's this transition between where you can identify these individual notes. They're spaced far enough apart where you can see them on the frequency response. And this part where they're so close together, it just looks like one thing, right? And you can no longer pick out those individual modes in the frequency response. That feel decent to y'all? Yeah. I mean, the best way to look at this, and maybe I'll kind of like make myself a little list. Let's look at what did I want to look at? Waterfall plots, right? Because they're worth looking at, and maybe a better picture of that Schrader cutoff frequency for you guys to see. Maybe when I'm done presenting this part, we can just pull that up a little bit and look at it together. But it's very much connected to this question before, right? This estimates the total number of modes. Those modes are going to be very spread out at the beginning and very close together as you get higher up. The part where they're close together is the statistical part. The part where they're further apart is the modal region, right? And the Schrader frequency is just the dividing line between those two regions. I'll leave it there for now. We talked about this, but let's make sure we're there. If the T30 for a room was measured to be 1.5 seconds, which of the following times would you expect to be closest to the T60 value? Explain your reasoning. How does T30 relate to T60? We talked about this like a billion times now. That's exactly right. It's just an estimation, right? You want to get clever about why you need it. It's because sometimes the noise floor in a room is such that you can't reasonably get 60 dB above it for an excitation. So you don't actually know when you get to negative 60 dB. You don't know when it's dropped because it's below the noise floor, right? So you have to estimate it. And if you can't do that, then you have to use the T10 or whatever that was called, right? There's a whole nother one, right? But the T30 is just a tool you can use to estimate T60, and it's a very simple tool. All it says is that if it takes 1 second to drop by 30 dB, then it takes 2 seconds to drop by 60 dB. So the 60 dB. So the T30 in that case is 2 seconds. Yep.
Oh, so like, I was under the impression that the value of T30 here is 1.5.
Mm-hmm.
Describes what the T60 actually measures, so that they would be, kind of the same.
Yeah. They should.
Just for clarity, is this 1.5 seconds describing the drop in 30 dB?
No.
Here?
No, it's just so it's a little bit weird.
By 60 dB.
It's by 60 dB. It's double what you actually measured for 30 dB.
Right.
So what you measure for 30 dB is not your T30.
So
Your
this is
T30 is double what you measured for your 30 dB drop.
1.5 is not like T30 in this case. Is that what I'm
So T30 is 1.5 seconds, but to get that 1.5 seconds, and maybe it's confusing the way it says it, you actually measured 0.75. That's already been multiplied by 2.
Right. Yeah, that's what I figured.
Yeah.
It's just like, I don't know, sometimes
It's weird.
no, it's
If they just called it a T60 prime, nobody would freak out. But because it's called a T30 and we're so explicit in the way that we measure it, it ends up being more confusing, right? But it's just an estimate, and it's a very simple estimate. You just measure how long it takes to drop by 30 dB. You don't report that. That's nothing, right? You double it, and that's your T30. And it should be about the same as what you got for your T60. Cool. All right. I think that gets us through homework. Did anybody on the internet or IRL have questions about anything we just went over or stuff from last week about homework 5? Yep.
Yeah,
Was that Eldrin?
yeah, it was.
Yeah, give me
Sorry,
like,
I just had one
no,
question
no,
about.
you're all good. Can I do Jung Woo and then Corey and then you're up? Is that cool?
Yeah, no problem. I'm here.
Okay, cool. Jung Woo.
For 3A,
Yep.
can I also like brute force this on MATLAB using the little like F equals like C or like that thing?
You talking about 3A, just getting this number? Yeah, absolutely. Do it in MATLAB. I do everything in MATLAB.
I mean, like not using that equation, but
Oh, like counting them? Oh, yeah, I see what you're saying. Yeah, you could. It's just gonna, so you're saying like, could you just run it, right? And iterate through every possible permutation, every different mode, right? And count them up? Yeah, but you have to know, there's a rule about that spacing that's somewhere here in this math, I suppose. And you have to know what that rule is, because it's, it's or no, this is sorry, never mind. This is not the Schrader frequency. Yeah, you could just count them up. I think it would be, I think it would take you a long time to run it potentially, but you absolutely could.
I don't know which rule was wrong, but my results disagreed with.
By how
each
much?
other.
But like a factor of what, without revealing what you actually got?
By a factor of some kind of 60%.
Seems like a lot. Can we look at it after class? Because I think that's a decent question. It should be a pretty close. I would imagine within like, I don't know, like a few modes. You know what I mean? Yeah, of course.
It's kind of going off that. When I am considering these possible modes, in this case, we start at 1. Like my for loops should iterate from 1 until whatever number M, L, and N. Or do they start at 0?
They start at 0. I mean, 0, 0, 0 isn't anything, but you have to have 1, 0, 0, 0, 1, 0, 0, 0, 1. Yeah. So you do have to start at 0.
Got it. That's at 0 or what?
Say it again. No, they start at 1 to be as difficult as possible. Yeah, you have to sneak that in, right? You can't index like that. You have to subtract 1 or whatever, right? Or just not use it as an index. Do you want to see how I did it in MATLAB? That helpful?
I mean, I don't know. It seems like not so difficult, but I'm not getting the right answer.
Let me.
That's a big part of it, is that it wasn't starting at 0.
Yeah, that absolutely might be the issue. Yeah, you have to do, I will tell you this, if you treat it like binary, right? So 3 digits binary is 7 permutations, right? If you run all those, you should get what you need. The first 7. Shouldn't need to go much further than that. You know what I'm saying?
I do know what you're saying.
So that would be only using 0 and 1s. Well, let's look at it. We can look at that together, and I'll look at Jongwoo's MATLAB as well. Okay. But I can also show you how I did it if anybody's curious. I like sat at it and looked at it, and I was like, I'm going to do this with nested for loops and be all sneaky and hack the mainframe. And I couldn't get it. Like I eventually gave up, and I made like I made a vector of the different ones that I wanted.
It makes me feel better because I'm like sitting here trying to
Yeah, it's so you can do it if you only have 2 dimensions.
Yeah,
and that's what I did. But it's yeah, and then you're like, how am I going to look at this? Because of what I want it to do is just say, like the first 3 columns to be like 0, 1, 1, and then a number, right? And I couldn't, or like it just was such a hassle. I was like, maybe I'll just do it in binary and I'll tell it to, iterate in binary. But then like you can go to binary, but then it makes it a binary in MATLAB is not actually a number. It's like anyways, I digress. The point is you can do it like a dummy and it still works. Eldrin, what's up?
My question was just for the relationship between T30 and T60. My phone was breaking up a little bit between that.
Yeah, let's talk about that because it does get mad confusing. So it helps. I think a drawing is in order here. Okay, so let's do this. Okay, this is just the signal level in the room. Okay, that we're looking at. So this is dB, and this is time. Okay, so I'm expecting this to be pretty linear. What I would like to do, let's just call this point -60, and let's call this point 0, all right? What I would like to do in a perfect world is I would like to excite this room with an impulse at 0 dB, and I would like to watch it decay all the way out to here, and then this point in time is my T60, right? You with me on that?
Yes.
Okay, cool. That's my T60. It's just the time it takes to drop 60 dB. That simple, right? However, oftentimes, right, maybe I have noise in this room, and let's put that noise at -40. Well, what's going to happen is if I excite this at 0 dB, right, it's going to drop linearly until we hit -40 where the noise is, and it's going to flat top, right? It's never going to go below that because this is all noise, right? So even though the excitation has dropped down, right, what I'm measuring with my microphone is stuck at -40. You with me on that?
Yeah.
Okay, cool. So what do? I got to figure something out here. One thing I could do is be like, okay, let me just excite this room at +20, right? And then when it gets to the noise floor, I'll have dropped 60 dB anyways, and I'm good to go. The problem with that is it may get unrealistically loud, your excitation. You might be stuck. You just can't get it that loud without distortion or whatever, right? So what you have to do is go out here, measure the time. Let's call this 2 seconds to make it easy. Measure the time it took to get here, okay? This is 1 second, right? Okay. The important distinction here is 1 second is not my T30. My T30, what am I drawing here? My T30 is 2 times whatever I measured here, which was 1 second, equals 2 seconds. So they're the same, right? The reason that it even exists is because I'm trusting that this decay is perfectly linear here, right? If it's actually a little bit different, right? If I have some behavior that's like, I don't know, like this maybe, right? Or whatever, right? If it's not perfectly linear in some way, then this and this won't be equal, right? So it is just an estimation, and you do it when you only have 30 dB of headroom in a room. But the value at the end should be the same. And where people get tripped up is they want to be like, oh, your T30 is 1 second. No, I measured 1 second at 30 dB drop, but my T30 is 2 times that, gives me 2 seconds. Does that feel okay?
Okay. So yeah, I got that. And but the part that is tripping me up is why is it the 2 seconds? I get the 1 second where it falls on the linear spectrum, but sorry, why do we have to multiply by 2?
Because what we're looking for is an estimation of how long it would take to drop by 60 dB, right? Even for my T30. The T30 is an estimation of how long it would take to drop by 60 dB. The T60 is actually how long did it take to drop by 60
Oh,
dB.
okay. Sorry. So wait, all right. Let me
No, you're all
one more
good.
time. One more time.
The
So the
name is very
T30,
confusing.
we're using T30 to estimate how long it would take to drop to T60.
You got it. That's exactly right.
Gotcha.
Okay. Cool. Other questions on this homework type stuff? Yeah, for sure. 2B. Oh yeah. So this is our bass trap thing. And we want to know what what wall we're going to build this thing on, right? So coming back to the example we were using in this room, let's say that the 1, 0, 0 mode is the one that I'm interested in. And let's call the x direction this axis, right? From my left to right. Cool. What that means is that there's a pressure pattern, let's say, that goes, I mean, it doesn't matter where you start or where it's high and where it's low, but it's half of a cosine wave, right? And it goes like that, right? It's at 1 there and at -1 over here. You with me? This shape, that half cosine shape, okay? In the other two directions, so these planes, right? Any plane like this, right? Those sort of ZY planes, right? There is no pressure dependence. It's the same. If I take any of those slices, the pressure is the same, all on that plane, right? Because pressure doesn't depend in this case on Y or X. Sorry, Y or Z. Cool. So where do we want to build this thing? Well, we want to build it, and let's do a little drawing here. We want to build it at an antinode. And if we go back to a string, right? So here's my string. Let's do the n equals 2 mode of this string, right? If I wanted to, take energy out of this system, right? Or add energy in for that matter, where would I, or let's say this, if I wanted to pinch this thing to stop it from oscillating, where would I do it? Would I do it here? Would I pinch right there to stop this thing from, no, it'd be here at the antinodes, right? Yeah, okay, cool. So those antinodes, those show up on that wall and on that wall. You with me? It's the same deal, just in 3 dimensions here. Does that make sense? Does that feel like a better explanation? Okay, cool. This homework. Anything else? Let's blast through a little bit of test prep stuff. You guys got a test on Thursday, right? Okay, so I think we beat this homework to where we want it to be. So let's jump out of here and go to, get in the Wayback Machine and go to homework 3. Ugh. Okay, we're just gonna cruise through this, right? And anywhere I see something that I want to tell you, I'm gonna tell it to you. And anywhere you see something you want to know, you're gonna ask me, okay? All right, here we go. Calculate so this is a rectangular membrane, says calculate the resonant frequency of fundamental resonant mode and identify the mode with the second lowest resonant frequency. There's nothing to this. This is an equation which will absolutely be on your cheat sheet, right? Right? The frequency of modes in a rectangular membrane. Done and done. Put that on your cheat sheet. Know what the different things are, like that sigma and the tension, right? I did a better job like later in some of these materials where I tell you, I make sure you know what everything means below it, but make sure you do, because I think it would suck to have this equation on your cheat sheet and be like, I don't know what sigma is though. You know what I mean? Okay, there you go. If the membrane was a circle with fixed edges, determine the radius needed to get the same fundamental frequency. Know how this works. Look at your Bessel zeros table, right? Practice this. Know how this works. Know what these modes look like. You know what I mean? So I was gonna post my code for a circular membrane where you can just choose what mode you want to see, and you'll see just that mode. That'd be helpful to you guys. The point is, I want you to have some intuition about like what a mode's going to look like, what the 0, 1 looks like, or whatever. So I'll put that up there. You can use it if you want to. But I think it's a good way. You can just test yourself. Be like, do I know what the 0, 3 means? physically, right? Because remember, we have these, and I'll try to pull up this MATLAB in a second, but we have two things going on here. We have these radial nodal lines, right? Like this, where it's like, you know, 1/2 of it or whatever is going up and the other half is going down, right? And then you also have these like nodal circles, you know what I mean? So know where each one comes from and be able to draw this stuff. There's something I noticed in the notes where it's like, now I'm forgetting which one's M and which one's N. Zeros. So we'll look at this here in a second, but I think the nth 0. So I think N is going to determine, yeah, I think N is going to determine the circles and M is going to determine the nodal, radial nodal lines, right? But there's a part in the notes where it's like, if you have, so the number of your N is, that's how many circles you have. And the number of your M is how many lines you have. And that's not quite true unless you count the outer edge as a nodal circle. So just be careful with that. Because this, with nothing in there, that is N equals 1, right? With nothing. So we're counting this one. This is N equals 2. Just be careful, okay? You know what I mean? I don't want you to see like N equals 3 or whatever and try to fit 3 plus the outer edge. So that's not how it works, okay? Well, we'll look at it in MATLAB. It'll probably make more sense. If we were just interested, blah, 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 blah. What do modes look like? Yeah, I want to look at that here in a second, but we'll come back to it. In a few sentences, explains what it means for two modes to be degenerate. What's the deal with degenerate modes again? Yeah, so you have two modes, the same frequency, right? Maybe the 0, 1 and the 1, 0 have the same frequency in your rectangular membrane. Those are degenerate, right? What shape has the most degenerate modes?
Square membranes.
Yep, boom, I love it. Yes, squares have the absolute most. You get more when one dimension is an integer of the other, right? If they're like not divisible by one another, they're not factors of one another, then you'll see fewer. Okay, what is the aspect ratio? Blah, 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 blah. Identify the 3 lowest frequencies. This is really a MATLAB question, so maybe we don't need to worry about it for the test. But it's, I mean, the question is the same as what we had up here, which is find the frequencies, the modal frequencies of a rectangular membrane. Drum hit stuff. Okay. That's actually okay for that one. So maybe we could jump to the next one and then open MATLAB for a minute. I kind of glossed over a few things on this one, but do you guys have any questions about this homework? Homework 3. Just make sure you have the equations written down somewhere and you're comfortable using a table like that Bessel function table, Bessel zeros. And then spend some time with that MATLAB program so you know what the shapes look like for different modes on a circular membrane, okay? Okay. So now what are we on? Homework 4? What order is this? Recitation 7, homework 4. I think this is right. Let's try it. Oh, yeah. So what do we got? Consider a plane wave propagating in air whose pressure in pascals is a function of space and time. As a function of space and time is given by this thing here. Determine the frequency of the oscillation in hertz. So just make sure you know how to read this thing, right? You know how to look at that and see what your spatial frequency is and see what your temporal frequency is, right? So 3000 is my my frequency in radians per second, right? And I can convert that into a frequency in hertz, right? Omega equals 2 pi f, right? All right. Yeah, that's right. Yeah. I don't want to say that wrong. Yeah, just know where stuff is in there, right? So basically, your 0.7 there is your peak amplitude, right? You can convert that to an RMS if it's a sinusoid by dividing it by √2. Know that, right? Know where to find those frequencies, the time frequency. There's got to be an actual name for that, and then so that 5.83, that's the wave number, right? But I like calling it a spatial frequency because that actually makes more sense to me, right? It's radians per meter is the unit, right? It's a spatial frequency, it's per meter. Okay. Define an expression describing the particle velocity, u x of t. That's just an equation. You can plug that in, calculate the RMS pressure amplitude. Make sure you know how to convert a peak value to an RMS value. If it's a sinusoid, it's just you're going to divide it by √2. That's all it is, right? And if you're ever looking at something in this form, right, this one here, then that first number is in its peak. Okay. Using the value for part C, compute the sound pressure level in dB SPL. Know how to do this sort of stuff. I mean, these are really just equations, but decibel measurements in general are worth just knowing how to do, and they're really just ratios, right? It always involves a ratio. You always have some reference, right? Even if it's implied, right? That's why we have things like in sound we have like dBVU or dB full scale or whatever. Those are references to those points. The Fletcher-Munson curve. Design yourself a little problem and figure it out. Time we got? Just want to make sure we have time. I'm not going to go over how to do that, but if you have questions, please let me know. Just know how to use it. More equations to write down on your cheat sheet. Nothing to really talk about there. Just put them there, right? Cool. A spherical wave is propagating in air at a frequency of 140 hertz. Determine the magnitude and phase of the acoustic impedance at a radius of 1.25 meters from the origin. We got more equations, right? We plug that stuff in, write those equations down, get them organized, right? Make sure you know what's what, right? But this is just the equation for impedance, spherical wave. Cool. You might practice a little bit with your doing stuff with imaginary numbers or complex numbers, like taking magnitudes and angles if you want to by hand, if you've always done that with MATLAB or whatever, or maybe just know how to do it with your calculator. You are allowed to use a fancy calculator, by the way, that might do some of this stuff automatically if you have one. Show that in general, the magnitude of the impedance of a spherical wave reduces to the specific acoustic impedance when the listening point is many wavelengths away from the origin. So it's the plane wave solution, right? It reduces to the plane wave solution. So know what the plane wave solution is for impedance, right? And it's, it's this, yeah, it even says that plane wave approximation, right? Just know what that is, what it means. You were swimming underwater in a pool, a friend yells at you, assuming your friend's voice behaves like a plane wave, normally incident, what is the ratio of the reflect? Oh, we're done with that, actually. That was on the next one. Any questions on that stuff so far? I know I'm just kind of cruising through them, but if you're like, oh yeah, I remember I screwed that up on the homework, then ask me and let's go over it together. No. Okay. 7. 4, Q3, right? Oh yeah, here's some good equations for you. So we've got how to find the speed of sound in a medium. You have a bulk modulus and an equilibrium density. There you go. We have the plane wave impedance, which is what we were just talking about, right? That's the impedance for a plane wave. And then there's this bad boy that's going to tell you how much of a wave reflects, right? And just know how to use R. R is going to be, what it's going to give you is a ratio, right? It's going to give you something like 0.4 or whatever. And then you're going to multiply that by the level of the incident wave or whatever. You know what I mean? It's not going to spit out for you exactly what the value is. It's just going to be the ratio of those two values, right? Definitely have that written down on your cheat sheet. We got angles, we got Snell's law. Yeah, all sorts of fun stuff here. A lot more equations that you should write down. Trying to think if there's any more like sort of theory stuff we can talk about. Yeah, maybe draw one of these out for yourself. I don't know, I probably would, right? Draw one of these and label this angle. Yeah, you know what I mean? Just so you can look at it. Okay. Know the del squared operator. That's a hint. Okay. There are some things that know the del squared operator. Put that on your cheat sheet. Okay. Nothing. I've done the test. It's not super scary, right? But that's one thing I guess that you might not have automatically put on your cheat sheet because mostly we did that stuff in class. Okay. But just know what it is. Okay. And then I want to open, or any more questions on this homework 4? We went through that very, very quickly. Anybody see anything that looked confusing? No? Okay. I want to look at MATLAB shapes. Oh, I want to show you a couple things in MATLAB. So let's stop sharing. Internet folks, you guys got questions, yell them out. Okay, let's look at, so this is the code I wanted to put up for you guys if you want to use it. So this is modes on a circular membrane and how they end up looking. So this is m equals 0, n equals 1, right? So this is what I was talking about, how n equals 1 here, which according to your notes would say that there is one, I think there's a part where it says like, that means that there's one circular, nodal circle, I guess. Do I have any of these? Okay, right? But the way that you'd actually draw that, right, is this, right? It's like, it's not a sine wave, it's like half of that Bessel function, right? But like the whole thing goes in and out. You don't draw it like that, right? That's not correct, right? There's no nodal circle right there for this one. You with me? That cool? If I want to see that, I actually need to go, and that's what I meant by counting this outer ring, right? Because that's a node, sure, it's a nodal circle. It's just at the edge, right? Oh, you guys aren't able to see this, are you? You should have told me. Come on, man. Okay, let's do that. You're not gonna be able to see the board, but that's okay. Share screen, desktop, share. Let's run that again for you guys. Okay, so this is m equals 0, n equals 2. So this you actually draw like that. You with me? There actually is that nodal circle in the center. Internet guys, if you want me to show you what I'm talking about, I can in just a minute.
Say that one more time. That's n equals 0, m equals
This is m equals 0, n equals 2.
n.
Yeah, the n values are going to give you the circles. The m values are going to give you the radial nodal lines, okay? But do you guys get my point about the way that you actually draw these? Just count the, yeah, feel it. Just count the edges and you're fine, okay? So let's go back here to n equals 1. Let's go to m equals 1. There is no n equals 0. It's not a thing, right? So now do you see how you get that line in there? So that is now the way I would draw that flat would be like this, right? And then maybe I'd shade in that part, tell you they were out of phase, okay? But that thing is vibrating or short vibrating like that, yeah. Okay. If I want to make another one of those bad boys, I can, another radial nodal line that is by doing this. And now it gets harder to see what it's actually doing because it looks like it's like inflating. Now we get this. Okay. I'll put this up, play with it. My suggestion is just to know how to how to use those Bessel zeros, how to find a frequency, right? How to find the frequency of a mode, and how to draw them like this, right? Know what they're going to look like. Be like, oh yeah, that, you know, I can see that, and I can be like, yeah, that's m equals 1, n equals 2. Yeah. No, that's m equals 0, n equals 2. Okay. No, m equals 1. God damn it. I mean, gosh darn it. M equals 2, n equals 1. Is that sorry. Yes, n's are the circles. N's are the circles. M's are the yeah, I would definitely put that on a cheat sheet. What else did I want to show you? Oh, do you want to see how what I ran to find those numbers? Let's make sure I'm not giving away too much here. What is this? No, that's something else altogether. I don't know where it is. I just put everything in an array when I ran through those. And Corey, I'll just look at yours with you here in a second if you're around. Oh, this is nonsense. This isn't it. This is if you want to this, you know what this is. This is spectral envelopes with LPCs and capstrums. Yeah, different class. Also worth knowing. Here, let me see if I can find it. I just don't want to make sure, I don't want to share anything by accident that I shouldn't. So hold on. Let me stop share. You guys are still going to be able to see it. Okay, homework 5. I got too much junk open. Homework 5, shouldn't that be it? Yeah. Oh, yeah, here's what I did. Let's just change. There we go. Okay. So I'm going to make that bigger so you can see what I did. I'm going to share the screen. So this is all I did. You see the matrix I made? It was that. It was that dumb.
Okay, yeah, that's
Is that about what you did?
no, that's what I was thinking I was gonna do, and I was like, I could just do this right here, so that I could have
Probably way faster than what it was for me. I was gonna do, I told you I was gonna like hack the mainframe. It didn't work. But this approach out it will work just fine, and it'll give you the numbers you need. Okay. Let's stop that share. What else did I want to show you? Waterfall plots, that can what I'm going to do is, internet folks, I want to show you what I was writing on the board real quick about those nodal lines and how to draw them, because that's pertinent. And then anybody with specific questions, just hang out and we can talk more about stuff, where I can look at your work specifically if you'd like. Okay. But I think that's the last thing we'll do. That's like kind of like everybody. Stop share. Okay, this is fine. I'll just draw it right here. Okay, so all I was showing those guys, internet folks, is that if you have, Corey, make sure I get these letters right. When I say N, I mean N, okay? If I get it wrong, tell me. So my N's are my circles, right? And the point is that if I'm drawing this like this, you might read in your notes where it says, the value of N is the number of circles that you need. And that is true, but you must count the outer edge as one of those nodal circles, right? I have just drawn N equals 1, M equals 0, right? This is, I'm pretty sure I got all those right, didn't I, Corey?
I hope so.
Yeah. We're 1000% sure. There's no chance this is wrong. This is M equals 0, N equals 1, right? That's that. So if I want to draw N equals 2, right, that's going to be like this, right? And you just saw that in 3D, right? And all the point I wanted to make is that, yes, the value of N is the number of circles you need, but you must include that outer circle as a nodal circle. All right. Then let's go ahead and let's add a let's do this. N equals 1 is right here. Okay, so I've already drawn that, but let's do M equals 1 now. And that, my friends, will get you one of those. Okay. That is a radial nodal line. Okay. And if I had M equals 2, I'd get that, right? And maybe I'd shade these like so. That's all I was showing them. I wanted you guys to see it too. Questions from the internet about anything? You guys are good. You're gonna all get 120%. If you run into questions about anything, send me an email. You don't take this test till Thursday, but your homework is due tomorrow during class, before class. Cool? All right, you guys. I'll post this stuff as quick as I can. Bye. Have a good one.